Right. In this video, our aim is to provide a proof for this lemma you see here. So we have the situation that we have a Lie group G with a closed subgroup H, and we want to consider the quotient space where we have G mod H, a set which we call the coset set or the coset space. And we want to endow it with the quotient topology with respect to the map Q, which is a map sending a group element to the coset of this group element. And by definition, the quotient topology is the topology which is defined in the following way. We see this in this yellow box here. If you have a set, then the set inside of the coset space is open if and only if its pre-image under this quotient map is open in G with respect to the original topology. And the claim of the lemma is the quotient topology is Hausdorff topology and Q is an open and continuous map. Okay, so let's see how the proof goes here. Uh, so first of all, note that the quotient topology is the final topology with respect to the family of maps, well, which consists only of this quotient map here of the Q. So in particular, from our knowledge on final topologies, we know that the quotient topology is a topology. Okay, great. And now let's ponder for a moment what does it mean for Q to be continuous. First of all, a continuous map is by definition a map where such that for every open set in the target space, the pre-image of this open set is open. But if we are reviewing how the quotient topology is defined inside of the yellow box, so we see that all the open sets in the coset space, or all the open sets with respect to the quotient topology, are actually defined in the way that their pre-image needs to be open with respect to the topology in G when I take the pre-image under the quotient map. So automatically, Q is continuous. Okay, great. Let us see now that Q is an open map. For this, we take O, an open subset of G, and we want to see that its image under Q is open. So, well, to see that the image under Q is open, we basically have to compute the pre-image of this image and see whether this is open. But by definition of what this quotient map is doing, that it sends every element to its coset, we have a formula for this pre-image. So this is just the set O, and then we have to collect all of the elements which lie in the coset with respect to this. So this is the set O times H, or in other words, all the products of elements inside O with elements of H in that order. And we know that this is open since in any topological group, if I have an open set and I take the products with any given set, so whatever the H might be or what topological properties it might have, as long as it's a set, this is uh, such sets are open. By openness of the O. Okay, great. So we see that the Q is a continuous map. It's an open map. There's just one final thing. So final thing to do. Prove Hausdorff property. of the quotient topology. So this is not obvious. For this, we basically need to distinguish different cosets with open sets. So let's just take 2 points such that the coset of one of them is not equal to the coset of the other. Note that this actually is equivalent to G1 not being inside of the coset of G2. Okay, so we have this, and now by a similar argument as to why the O times H was an open subset with O open, so since the H is a closed subgroup, since H is closed as a set, G2 times H is a closed subset. Okay, and now we use a technical lemma from topological group theory. So in case you want to see how this proof goes, check out the video detailing that. However, so this technical detail was lemma B03 in the lecture notes. Shows that there is an open set which contains G1. So we call this open set U, such that if I intersect U with G2 times H with this closed set which does not contain G1, this intersection is empty. Okay. Okay, and with this we go further. So pick a symmetric unit neighborhood. So let's call this one U1. Let's say that in addition, this should be open in G, such that if I take U1 inverse, I mean, we are again using the set notation, U1 inverse times U1 times G1, I want this to be contained in U. Let us now consider the sets U1 G1H and U1 G2H. First note that both sets are open. Since Q is an open map, we see that well, Q of U1, let's do this directly general for Gj times H. So this is open in the coset space and contains the element Gj times H, so the coset with the Gj. Okay, and if we take the preimage of this open subset, because those already are basically containing all the cosets, so we see that we get back the set we started with by definition of the quotient map. Okay, and what we have to do now is we basically have, or we want to see that the intersection of these guys here, sorry, G1 and U1, G2, H, that this is empty. So let's assume we have an element in there. So let's say we call this element again Y. So today the element is called Y, and then we know that we can write Y in two ways. We can write it as U times G1 times H, but we can also write it as V times G2 times H, let's say H tilde, where U and V are in U1 and H and H tilde are in the subgroup H. Okay, and now let's sort this out a little bit. So I can basically reorder these things and I can write, so the G1 is now U inverse times V times G2 times, sorry, wrong way around, of course. Actually, I want to sort it in the different way. So I want, so I have G2 times H tilde times H inverse. So there we see that this is inside of G2 times the subgroup H. And now I'm looking at the equalities before, what this is equal to, on one hand we have G1, and then we have V inverse, and then we have the U. So this here, since since V and U are both in U1, so this is inside of U1 inverse times U1. Okay, let's see what U1 inverse times U1 times G satisfies. We have set it up to actually satisfy this inclusion. So if you have U1 inverse times U1 times G1, we are inside of U. So the right-hand side here is inside of U. So basically, if such a thing exists, then we have some element Y which lies in the intersection of my open set U with G2 times H. Okay, let's see that this is impossible. Well, basically, it's impossible because we said that the intersection between those two sets is empty by construction. So this is a contradiction to U intersected with G2 times H. It has to be the empty set. Okay, and what we see here is now that since such a thing does not exist, we see that indeed, as we wanted it to be, that the intersection of U1 G 1H with U1 G2H needs to be the empty set, and this implies that the sets Q of U1 G J H. So those are open neighborhoods of the cosets we were looking at. So they are disjoint. And now we basically established the Hausdorff property, because in the Hausdorff space we need to find open subsets which contain the two elements, namely the cosets we are looking at, which are disjoint. Since these elements were arbitrary, we can basically we have established the Hausdorff property, and this completes the proof.